Hello and welcome YouTube, Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside, we got a little review for you guys, section 6.1 to 6.4 from the Big Ideas Math Integrated Math 2 textbook, what they call a quiz. You can check out the PDF down below in the description section, as well as a timestamp for each individual problem. It shows only 14 problems. I'm kind of excited. I hope they're not very long, personally. 6.1 was proving certain geometric properties. It had things with right angles, like right angle proofs, corresponding angle proofs, vertical angle proofs, alternate interior angle proofs, little things like that, just basically dealing with proofs, getting you the good reminder of how those things work. 6.2 was on perpendicular bisectors and angle bisectors, very specifically their theorems. Perpendicular bisector theorem, angle bisector theorem, I'll cover those if they talk about them here. 6.3 was bisectors within triangles and talking about the circumcenter and the incenter, and we'll talk about those if we run into those. And 6.4 was about medians and altitudes of triangles, where we got to talk about the centroid and the orthocenter. So all those things come into play. Sometimes we use things with graphs, sometimes we use things with compass construction. We'll see what comes into play. I haven't done the problems yet. I'm excited to, though, and I hope you guys are too. Let's go ahead and take a look at what we have going forward right here. Excuse me. Number 1. Oh, I didn't do a little circle thingy. Give me a second. I never did that. Time out. There we go. Okay, we're ready to go. I was like, something's missing. That's it. Numbers 1, 2, and 3. Out of section 6.2, you can see where it says up top. That's more about perpendicular bisectors and angle bisectors. Find the indicated measure and explain your reasoning. It would probably be best if I did a little bit of a copy and paste of this. It might be a little blurry when I enlarge it, but here we go and show you what we got going here. So on number 1 with this figure, what you do have and what you're looking at is this line VW, and remember, it would extend all the way through T. Ideally, it would extend all the way through T. It is a perpendicular bisector of the segment SU. And we know that because they show these marks here. They show congruent marks here for these. That means W is the midpoint of segment SU, and they show the right angle. That means it's perpendicular to it. So being a perpendicular bisector, they want to find the indicated measure. They want to find the length of segment UV. Now, in order to do that, what you want to take a look at here is the perpendicular bisector theorem, which states that any point on a perpendicular bisector of a segment is equidistant from the 2 points, from the 2 endpoints of that segment. So point V is on the perpendicular bisector. We know that for sure. Technically, T would have been as well if this line kept going upward because of the equidistance here. That's the converse of the theorem, but that's neither here nor there. V is on the perpendicular bisector itself. Therefore, it is equidistant from S and U. Therefore, these segments are congruent. Therefore, their lengths are equal. Therefore. What we can do is set 2x plus 11 equal to 8x minus 1. Let's solve for x. Subtract 2x from both sides, add 1 to both sides. Divide both sides by 6, we get x equals 2. Now that gets the length, that gets x. The length of segment UV is by substituting 2 for x into there. So UV would equal 8 times 2 minus 1. 16 minus 1 gives you 15. 15 units in length is UV. That would also be the same for SV. Now I did mention that length TS and TU also are the same distance away, and you can tell they marked congruent segments for you. If we don't run into it, the converse of the perpendicular bisector theorem states that a point that is equidistant from 2 points of a segment is on the perpendicular bisector of that segment. So like I said, W and V are collinear with T. The line would go through T if we used it. We're not. Not for this problem. Number 2. Number 2 is in reference to angle bisectors and something regarding the angle bisector theorem when we find the length of QP. So on number 2, I don't think I'm going to put up the drawing this time anymore. I can just refer to it here. But you see these 2 markings right here. There's a congruent arc mark right there for angle PSQ and for angle RSQ. That means these 2 angles are congruent to each other, which means ray SQ is the angle bisector of angle PSR. It divided the angle into 2 congruent parts. Now, the angle bisector theorem states that a point on the angle bisector is equidistant to the sides of the angle that it is bisecting. The distance that they're referring to is the shortest distance, which is the one that's perpendicular to there. So that's why when you see these little perpendicular marks right there, That's the closest that Q can get to this side of the angle, SR, and that's the closest Q can get to the side, SP, right there. So these two would be congruent because of that equidistance, and congruence means equal length, and yada, yada, yada. So that means that the length PQ, and I should have done this for the other problem, but that means that the length PQ equals the length RQ. They are both equal in length. Therefore, 6x, which is the length of PQ, equals 3x plus 9, which is the length of RQ. Subtract 3x from both sides and divide both sides by 3. You get x equals 3. We're going to use that to find the length of QP. QP is just one of those two lengths. You can technically substitute it for either or, but let's just do it for the expression that's QP. 6 times 3 is 18. 18 units in length is QP. That is the angle bisector theorem. Number 3. We're going to find the measure of angle GJK given this situation. Now, when you look at this drawing, do not make any assumption that GJ is an angle bisector. However, there is the converse of the angle bisector theorem. Just like the perpendicular bisector theorem has a converse, so does the angle bisector. This states this. A point that is equidistant from either side of an angle is said to be on the angle bisector of that angle, or is said to be on a line that would ideally bisect that angle. Now, this point appears to be equidistant by not only the congruent marks, but the reminder that we are looking at the shortest distance, so we can guarantee both shortest distances are the same by the right angles. So J is on what would be the angle bisector of this angle. GJ is an angle bisector. What does that mean? These two angles are congruent to each other, which means these two measures are equal. So again, I should have done it for 1 where I wrote the thing beforehand. I'll just keep doing it here on out. Measure of angle HGJ is equal to the measure of angle KGJ. Whoops. Because of the converse of the theorem. I'm only on number 3. So 5x minus 4 equals 4x plus 3. Let's solve for x and we'll find its measure. Subtract 4x from both sides, you get x. Add 4 to both sides, you get 7. That's x, not the answer. Measure of angle GJK? Oh my goodness, they want this right here. I didn't even expect that. So measure of angle GJK, this is the one that's wanted eventually. This guy right there. So check this out. We're going to do a couple things. Let's first find the measure of angle JGK. Now this is one of the bisected angles, like this 4x plus 3 right here. This is not the requested angle. 4 times 7 plus 3, that's going to give you 31 degrees. Now you may be aware that the interior angle sum of a triangle is 180 degrees. If you don't know that, I'm telling you right now. The interior angle sum of a triangle is 180 degrees. So the 90 degree angle plus this 31 plus this unknown should be 180. We can use that to solve that. However, because it's a right triangle, I want you to know that the non-right angles of a right triangle are also complementary, which means they add to 90. That makes sense. If 3 angles of a triangle add to 180 and one of them is 90, then the other 2 have to add to 90. What's my point? That the measure of angle GJK, why do I keep writing a J for G? GJK is going to be 90 minus 31. If 31 plus this angle is 90, then this is going to be 90 minus 31. Therefore, this is 59 degrees. That's the one that we want. That's the final answer. I don't know why I box things beforehand. I think just to say that I give reference to them later if I need to. But that is measure of angle GJK. That is number 3. All right, let's move on to number 4. Find the coordinates of the circumcenter of the triangle with the given vertices. Let me copy over a graph paper thing, and I hope that all these stay within the bounds of -10 to 10. No guarantees there. But number 4. We have A at -4, 2, B at -4, -4, and C at 0, -4. It sounds like some of these things will be kind of vertical and horizontal, which is nice when it comes to counting like horizontal distances and vertical distances, stuff like that. So A is going to be here at -4, 2, B is at -4, -4, and C is at 0, -4. So it's a right triangle as well. Let's draw that out. Let's see what we're dealing with respect to that drawing. What do they want? Circumcenter? I think so. Okay. Find the coordinates of the circumcenter. Okay, now a circumcenter. A circumcenter is by finding the point of concurrency of your perpendicular bisectors of your triangle. In a right triangle, the circumcenter will be on the triangle, specifically on the hypotenuse. It'll actually be on the midpoint of the hypotenuse, which kind of helps things. But if you weren't sure, let's kind of confirm that. Let's do the perpendicular bisector of segment BC. The midpoint between -4, -4, and 0, -4 would be -2, -4 right there. And its perpendicular line would be vertical. Let's make, sorry, I'm going to thin this thing out, make it dotted and green. So make a vertical line that goes through there. This is the perpendicular bisector of segment BC, going at x equals -2. For between -4, 2 and -4, -4 is the midpoint -4, -1. You can tell I'm not doing a lot of math to show that. Part of it's visual, part of it's kind of counting half those distances right there. And a horizontal line draws that one perpendicularly as well. Now, where do these intersect? These intersect right here at the point -2, -1. This here is your circumcenter. Now, the circumcenter should be what's the word? Concurrent? I suddenly lost the word. With all of your points that should all be perpendicular bisectors, meaning even the AC one is going to be that same one there that, you know, I don't need to draw the line though because it's on there, but it's on its midpoint. So that makes sense that it should be there. The circumcenter is at -2, -1. And that is the answer to part A. So perpendicular bisectors, where do they intersect? Remember, you only need 2 of them, but the third one was also the answer, which was kind of nice. All right, number 5. We got D at 3.5, E at 7.9, F at 11.5. 11 just overshoots 10. Shouldn't be a problem. We should be able to do some counting, but we'll see what kind of answer we get as well. No idea. No idea. All right, let's see. Normally I copy these points down, but if I plot them, I think that's going to be enough for us right now. Here's D. E is at 7.9. Or 7 right here, 7.9. And F is at 11.5. So the same height as D. F is going to be there at 11.5. I think that's going to work out. Okay, so let's draw. Oh, didn't fix that. Let's draw a couple segments for this triangle. Right there. And let's concoct some midpoints. Truth be told, this looks like another right triangle, which is interesting for a quiz, like a review thing. Why would you have 2 different right triangles? But it looks like that's exactly what we have. This looks like this is a slope of 1 and a slope of -1. So I believe it's another right triangle, which means this circumcenter should also be on the triangle, on the hypotenuse. Now, I was going to straight up go for this midpoint here from 3.5 to 11.5. That's going to be at 7.5 right in the middle. And then the vertical line is going to go straight up into here. Fantastic. However, I think this is also the circumcenter right here at 7.5. We'll find out soon enough. Looks like it. So check this out. Here's how we can work some of the other ones. I mean, even if you did know that, let's just talk about how you'd find some of these other ones here. This midpoint is halfway in between. This goes up 4/4, and go half up 2/2. Find a midpoint there. Heck, you could do it for this one as well. Let's find all 3. Now, perpendicular lines are opposite reciprocal slopes of these. If this slope is positive 1/1, then you flip the ones, which means nothing. And you get a slope of negative 1/1, and then it goes this direction right there. You can see where it's going through, the circumcenter. And then this thing does the same thing, as a slope of -1. The opposite reciprocal is a slope of positive 1. What does it go through? Le circumcenter. So there's your circumcenter right there, which is at 7.5. So I don't know why, and hopefully this isn't the only circumcenter review. Well, sort of, maybe, hopefully. We're already 5 out of 14 down, a third of the way. Both of them were right triangles. Kind of a bummer. Just so you know, in an acute triangle, the circumcenter would be inside the triangle. In an obtuse triangle, the circumcenter would be outside of the triangle. That's also true. All right, let's go to numbers 6, 7, and 8. Also from 6.3, but looks like they're going to talk about incenters. The incenter of triangle ABC is point N. Use the given information to find the indicated measure. By the way, I'm probably going to speak more about what a circumcenter is after this because it's unlikely we're going to get to talk about them again. Okay, incenter is point N. for all three of these. N, 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 the N, N. Use the given information to find the indicated measures. NQ is 2x plus 1, NR is 4x minus 9, find the length of NS. Okay, so for these ones here, an in-center. An in-center is the point of concurrency among the three angle bisectors of a triangle. So you draw an angle bisector here, here, and here. They are concurrent at this single point N. Now, what an in-center is very cool with is it is equidistant to any sides of the triangle. And remember, distance is measured by the shortest distance, so the perpendicular one. Basically means you could inscribe a circle inside of here. That's what I wanted to, before I keep moving on, that's what I want to say about a circumcenter. The circumcenter is equidistant to all vertices of the triangle. That means that, I'm going to just draw these deep red. That means that this distance, that's too deep of red. That means that this distance, and this distance are all congruent because they go to D, E, and F. This is the bad part about doing it on a right triangle. That's the only thing you could see. And then same thing with this right triangle. This distance, and this distance are all equal as well in that same way. So that's what a circumcenter does. You can circumscribe a circle around that triangle, and an in-center, you can inscribe a circle. Circle can be drawn on the inside like that. It can touch all sides of the triangle, yada, yada. Okay, so that means all these things are congruent. Boom, boom, boom. They tell you NQ, this distance, is 2x plus 1, and R, this distance, is 4x minus 9. Well, those should be the same length. NQ equals NR, and guess what? It also equals NS. You know why that's important? We got to find the length of NS. It's going to be the same as these two. But NQ equals NR. Let's write an equation for that, given that we have 2x plus 1 for NQ. We have 4x minus 9 for NR. Let's solve for x. Subtract 2x from both sides. Add 9 to both sides. Divide both sides by 2. You get x equals 5. Now to find the length of NS, because it's the same length as these, you can either use 2x plus 1 or 4x minus 9, substitute 5 into there and get your value. No matter what, you will get 11. NS equals 2 times 5 plus 1, which is 11. Or 4 times 5, 20, minus 9 is 11. Either way, you're getting the same answer. That's number 6. 7 and 8 probably are going to be very similar in what we do unless they start playing with Pythagorean theorem stuff. We'll see. I like when they get tricky. Don't know if they will. Number 7. NU is negative 3x plus 6. Notice that that is this length. This is an in-center. NV is negative 5x. Find length of NT. So it's the same kind of ish. We know that NU, NV, and NT are all the same length. I'm going to go ahead and find the solve for x by using these two and their expressions that they have. We have negative 3x plus 6, and we have negative 5x over here. I'm guessing x will be a negative number in order to turn everything positive. I'm going to add 5x to both sides to give me 2x and subtract 6, get negative 6 there, and x is negative 3. All right, so negative x value. Let's find the length of NT by substituting negative 3 in one of these. I'm going to use negative 5 times because they're all the same thing in length, and we get 15. So same-ish, no real change on that kind of problem with number 7. Do some Pythagorean theorem. Let's go. Let's work it out. Number 8. We're halfway through, ideally, problem-wise. NZ is 4x minus 10. NZ is this guy. NY, this guy, is 3x minus 1. Find NW. Okay, so these are all kind of the same-ish. You do one problem, you've done them all. NZ, NY, and NW. New Zealand is the same as New York, is the same as the Northwest. Those couldn't be any further from the truth. All right, so I was going to say New Zealand. NZ is 4x minus 10. Maybe you get a fraction answer. NY, nope, is 3x minus 1. Subtract 3x from both sides, add 10 to both sides, you get x equals 9. So, I mean, really, again, there's no posed new challenge in the different problems that they ask you here. So, just go with it. And NW, let's do either or. Let's just do the back one. 3 times 9 minus 1. 27 minus 1 is 26. No units of measure in any of these. We're just going to go ahead and do it there. That's section 6.3 with in-centers. All right, let's move on to numbers 9 and 10. So out of section 6.4, find the coordinates of the centroid of the triangle. Of the triangle with the given vertices. Now, a centroid is the point of concurrency of 3 medians of a triangle. You intersect your medians, you have a centroid. So let's go ahead and do something like that. Find the centroid by finding them medians. We have J at -1, 2. K at 5, 6. L at 5, -2. Don't tell me it's another right triangle, because it very well may be. I mean, it's okay if it... Oh, you know what? It's not. It's very acute looking. It's okay if it is, especially for a median, but just no more. We've done our right triangles. Just looks acute. It might be equilateral. Who knows? All right. So for this one here, we got to find our medians. Remember, 2 will do. Actually, 1 could do, and I'll show you how, but I'll confirm it with more medians. A median is a segment from a vertex to the midpoint of the segment opposite that vertex. So for point J, we want to find the midpoint of KL and draw a segment from J through there. It looks like midpoint of KL is right there. I think you can kind of just attest for that, if that makes sense, right? So I can draw a median right here, J. I can call it something. I can call it JN or JM or something like that if you want me to. But this is going to be one of those medians. Now, there's more to a centroid than just this. A centroid also has, wherever the centroid is, it is 2/3 of the entire segment from the vertex to the endpoint, to the other endpoint of that median. So whatever this distance is right here from J, count 1, 2, 3, 4, 5, 6. 2/3 of 6 is 4. We can go 4 units away from J, not from this point, but from J. 1, 2, 3, 4, and boom, that would be your centroid. That will be your centroid. The point of concurrency for a centroid has that 2/3 relationship. 2/3 this way, or 1. You can do 2/3 or 1/3. They tend to talk about 2/3. I think it's more relevant to this stuff. They mention one of them. Anyway, to confirm this, check this out. Let's do another median. Let's find the midpoint of JK. Instead of going up 4 over 6, you can go up 2 over 3, and you have that midpoint there. So from L to that midpoint, meaning that median, you're going to have this guy here. Hey, look, it intersects that same place. That also means that this is 2/3 of the entire median. Now K's midpoint, if you can just take my word for it, JL's midpoint is over here, and the median from K to there goes over there, and you can see, boom, it hits the centroid as well. So that's the centroids relationship. It's not about drawing a circle within something, it's about that 2/3 thing. So this answer for the centroid is going to be at 3, 2. And again, it only technically took 1 to draw and take 2/3 of that distance. You could have drawn 2 and found the point of intersection. I did a bit of both, just to confirm it's there. Number 10, maybe we'll do a little less of that, unless there's something I gotta really calculate. So let's look at number 10. M, N, and P. So it looks like here they're using the different letters, and it looks like we're a lot in the third quadrant. So M is at -8, -6. N is at -4, -2. And P is at 0, -4. Could it be a right triangle? It might be a hair obtuse. We will find out. Oh, it's definitely obtuse. All right, what are we finding? Centroid. All right, centroid is, once again, 2/3 of the way in any direction. I really like using something like this P to here, and I think they really help you out. The midpoint from N to M, again, half that distance. Instead of going up 4 over 4, let's go up 2 over 2. Boom, you get that midpoint. So you notice when I draw P to there, it's horizontal. That's really, they kind of intend for that. They want that to happen. So you can probably just work that 2/3 distance. If, let's see how this calculates. Because the ones, honestly, the ones out of the problem sets were always like fractions, and this one maybe isn't. 1, 2, 3, 4, 5, 6. So 2/3 of 6 once again is 4. Now I'm going to go 4 units away from P, not from the midpoint, but from P right here. 1, 2, 3, 4, and boom, that would be your centroid. If you want to confirm it, let's do it one more time. The midpoint from P to M, you can imagine is going to be this guy right here, and I can draw a median from N to there. It goes vertical. Boom, it intersects with there. That's the centroid. Because it intersects with it, and it's 2/3 of the way. See, this distance is 1, 2, 3. What's 2/3 of 3? 2. So 2 away from N gets you to the centroid there. And then the midpoint between P and N is right there. Looks like I'm just doing everything just to confirm it. You can draw another median there, and boom, centroid, 2/3 of the distance. Not going to do more calculations to show you that, but there it is. Number 10. All right, number 11. I got 4 more problems to go. Tell whether the orthocenter is inside, on, or outside the triangle, then find its coordinates. So we got 2 things to do here. Now, an orthocenter is found by finding the point of concurrency of your altitudes of your triangle, of the vertices. Altitude is different from a perpendicular bisector. Altitude is drawn from the vertices. Perpendicular bisector is drawn from the segment, from the side. So here we got a t at -2,5. By the way, the orthocenter has no real larger purpose other than being called that, and meaning that altitudes still have points of concurrency for a triangle. It's a cool fact of life, but it can tell you whether a triangle is obtuse or not, or whatever, or acute, based on the fact that it has the orthocenter inside, on, or outside the triangle. Much like but in a different way, much like a circumcenter, if the orthocenter is inside the triangle, then you have an acute triangle. This one looks acute, therefore the orthocenter will be inside. Orthocenter is inside triangle. That just happens when you draw altitudes here when you draw altitudes. So it's inside the triangle. And what? And then find the coordinates. Find the coordinates of the orthocenter. So we got to find where they intersect. So how do you draw altitudes with ordered pairs? Keep in mind that an altitude is whatever is perpendicular to the side opposite, but it's drawn from the vertex itself. So for example, this segment TV is opposite of vertex U. I should be drawing a perpendicular line from U and perpendicularly through TV. Because TV is horizontal, U's perpendicular line will be vertical, which will look like this. I know you can't see it very much, but just kind of imagine there's a green dotted line that's going up and down like this. So the orthocenter is somewhere on this line. Now, I do need to draw another line to figure out which one's going to be. There is no 2/3 relationship or anything like that. I just know it's inside the triangle. So let's look at another one. Look at the slope of segment UV. The slope of segment UV, we go up 1, 2, 3, 4, and over 1, 2. So 4/2 or 2. 2/1. The opposite reciprocal slope, the perpendicular slope is the opposite reciprocal, which is -1/2. What you want to do is to draw an altitude through there, and from T, go down 1, right 2. It looks like it's going to hit that point right there. Down 1, right 2, down 1, right 2, etc. And then that should be enough for you to be able to draw that altitude that you're drawing. And definitely extend it if you're not sure where it's going to intersect through, but it looks like we can see that here. So this also happened to be the one that you went through also happened to be a perpendicular bisector of TV. That's not the intent to be perpendicular bisector, just be perpendicular. Like that one, it's perpendicular. This is your orthocenter. Orthocenter. Which is at 0,4. That is the answer to number 11. Inside the triangle as well. I didn't draw V, didn't really need to. Number 12. No fractions yet. I feel good about that. Don't press your luck, Mr. Robinson. Number 12. Few graphs. Definitely for 14 problems. What? We had 6 graphs? I just don't speak too soon. What about 13 and 14? I don't know. X is at -1, -4. X. Y is at 7, -4. Y. Z is at 7, 4. Looks like a right triangle. Yep. If it's a right triangle, the orthocenter will be on the triangle. This one really doesn't need a lot of work. Let me tell you about it. I kind of just need to draw this and I'm good. I need to just tell you that it's also on the triangle. Okay, let's kind of fix that. All right. Doesn't tell you to explain why it's on it, but orthocenter is on the triangle. Now, it's not only on the triangle. See, if you remember, circumcenter was on the hypotenuse of the triangle at its midpoint. The orthocenter is in a different place. Remember, it's all about where the altitudes intersect. Z is the vertex opposite segment XY. To go perpendicular to XY in a right triangle, you need to go down the leg. Just like that. Literally, this orthocenter is going to be at this right angle Y right here. If I draw an altitude from Z down to here, I know you can't really see that green dotted line that I just made, but I just drew an altitude from Z to the segment XY, down the leg there, and X would be the same thing, going that direction, like that. You probably can't see that, but the same right angle symbol could just appear. Boom. That's where they intersect. Boom. Right at Y. Heck, Y. Yeah, you would draw an altitude this way. Opposite reciprocal slope of 1 is -1, and you go that way with it. But where does it start from? It doesn't matter that you draw an altitude there. Where did this thing start from? That point right there. So this is the orthocenter. An orthocenter in a right triangle is not only on the right triangle, on the triangle itself, it's on the right angle. It's at Y's point, which is 7, -4. So I don't know if I really had to show work other than kind of confirm that that stuff works out the way it's intended to. That's what it is. Okay, two more questions, and we're only a half hour through. Number 13. Three parts, though. I don't know if we have to do, a proof. A woodworker is cutting the largest, I might have to copy this, cutting the largest wheel possible from a triangular scrap of wood. The wheel just touches each side of the triangle as shown, like an in-center would. Which point of concurrency is the center of the circle? I just answered it. What type of segments are BG, CG, and AG? All right. I don't know if copying this will help at all, but I'm going to point to what we're looking at there. Great. Okay. So number 13. A, which point of concurrency is the center of the circle? So the center of the circle is an in-center. If the circle inscribes the triangle, and these points are all equidistant from the sides of the triangle, this would be an in-center. What type of segments are BG, CG, and AG? BG, CG, it's these guys right here. BG, CG, and AG. To be an in-center, that is the point of concurrency of your angle bisectors. CG and AG are angle bisectors. Which means it's dividing the angles into congruent parts. That works with part of that angle bisector theorem. All right, number 14. Excuse me, number 14. Part B. I wish. Part B. Prove that triangle BGF is congruent to triangle BGE. All right, BGF is this guy, and BGE is this guy here. Okay, so you have, keep in mind, you do have right angles. I'm just going to kind of thicken what we have. We have a shared side, which we'll talk about, and we know that these guys are congruent. Wait, we can't, wait. Are we allowed to use that? Are we allowed to use in-center knowledge? I think so. Not so much in-center knowledge, but angle bisector theorem. Oh, yeah, angle bisector theorem knowledge. Totally. Wait. What stuff are we allowed to use? We're allowed to use the information we're given. So what are we given here? Hold on. We're not given it's an angle bisector, but we're given the perpendicular parts. We're given it's a circle. A woodworker is cutting the largest wheel possible from a triangular scrap of wood. The wheel just touches each side of the triangle shown. Okay, so we're given that it's a circle there. So I can use that to talk about congruency in these. They're radii of a circle. So, perfect. Okay, let's go ahead and start doing a proof off of that one here. I might have to provide the drawing a little. Well, you have the drawing on the left side there. So, statements, reasons. Normally, I'd copy the whole, like, given this, prove that, but we're going to go ahead and write them here anyway. So, statement 1, we can go ahead and say G is a circle. I'll say circle G is a circle. That's a given. Okay. Great. Now, E, F, and D are also on the triangle. So, I don't know if I want to say that. Triangle ABC contains points E, F, and D. All right. Okay, here we go. Now, circle G also has those points on its end. I don't know if we kind of have to use that, but okay. Let's go ahead and do this. We're talking about B. I'm going to show that GE is congruent to GF. Segment GE congruent to segment GF because radii of a circle are congruent. Right? Equal distance. So congruent measures there. So I have these two. Okay. We're also given, oh, by the way, here's just another given that I could just so happen to state. Perpendicular. It doesn't say perpendicular, just GEB is a right angle. Angle GEB, they have right angle symbols. And angle GFB are right angles. I probably should have said that as a thingy, as a given, but now I'm going to. Given. That allows us to say these are right triangles. Triangle I do these out of order because I don't really plan it with you guys. I kind of just write things. Triangle GEB and triangle GFB are right triangles by definition of right triangles. All right, now I have right triangles. I have two sets of legs in the right triangles congruent. I'm going to get the hypotenuse is congruent, which is that segment GB that's shared on both triangles. It's congruent to itself. Why would we say that, or how can we say a segment is congruent to itself? By the reflexive property of congruence, but the reflexive property. Shared side in both triangles. I have two sets of legs in a right triangle congruent, and the hypotenuse is congruent in the right triangle. Therefore, triangle BGF is congruent. This is my proving statement. It's triangle BGE using the HL congruence theorem. The hypotenuses are congruent, and its pair of legs are congruent in these right triangles. To show them a little bit bigger once again, I got a right triangle here with this right angle, and a right triangle here with this right angle. We found these are congruent. They're the radii of the circle. This is congruent to itself in a way, but those are the hypotenuses of the triangle. You have HL there, two congruent triangles. All right, that is part B. Part C. Find the radius of the wheel to the nearest tenth of a centimeter. Justify your answer. All right, well, let's look at this diagram a little more. Okay, so check this out. If these are congruent triangles, corresponding parts are congruent. That means that BF is congruent to BE right there. If this is 3, then so is this. If this is 3 as well, then that means that this guy right here is 7 because this whole thing is 10. 3 plus 7 is 10, so this guy's 7. So what I'm looking at, I'll outline it more for you, is a right triangle right here. That's a right triangle with a hypotenuse of 8. There's that 8. A leg length of 7 and an unknown length of x. This can be your radius. That can be your radius right there. So they said around to the nearest tenth for this thing. It's not like they want you to use a ruler. So I'm going to just go ahead and write it down here. So x squared plus 7 squared equals 8 squared. That's what we're going to go off of. Now that the congruent triangles allowed us to use that, that's kind of part of our justification. The math is the rest of it. So x squared plus 7 squared is 8 squared. X squared plus 49 is 64. X squared is 15, so x is the square root of 15 centimeters, and that approximates to, I have no idea, 3 point something. I'm going to say 3.8. 15, probably closer to 3.9. 3.87, so about 3.9 centimeters. They said nearest tenth? nearest tenth of a centimeter, justify your answer, yeah. So my justification is through the math. I CPCTC from congruent triangles there, showed if this is 3, so is that. All that jazz. Looks like we got to use all those things there. Okay, and that is number 13. Last question, number 14. Parts A and B. The Deer County Parks Committee plans to build a park at a point P, equidistant from the 3 largest cities labeled X, Y, and Z. The map shown was created by the committee. Okay, I might have to enlarge this one as well. You're going to get a little section where it shows that 14. That's okay. All right, part A. Which point of concurrency did the committee use as a location in the park? All right, well, this goes back to something I was talking about before. I didn't really get to talk about it in full. They said it's equidistant. Oh, no, that's not equidistant to X, Y, and Z. Hold on a second. Oh, it does plan on doing it from X, Y, and Z, but it's not equidistant from X, Y, and Z. So this is just not drawn to scale. I guess we... Okay. Anyway. Plans to build... I want to make sure I reread that. Equidistant from the 3 largest cities labeled X, Y, and Z. Yeah, those clearly aren't drawn equidistantly. We'll just go ahead and say that. Now, which did the committee use as a location in the park? They drew it from medians. Okay, I see. They're saying, which did they use and did they screw up? So they drew medians. I can see congruency here, here, and here, and clearly not right angles, or at least not drawn to be as such. But those things, medians were drawn through them. Therefore, P is a centroid. It's drawn from medians. Drawn from medians. And just by visual alone, you can tell that that doesn't seem to be equidistant. Did the committee use the best point of concurrency for the location in the park? If not, which point would be better to use? Explain. I don't think I'm doing math for this one. So what you want to use is the circumcenter. You want to find the one. So I'm going to type this one. This does not, the centroid does not create equidistance from cities? From cities X, Y, and Z. Instead, they should use the circumcenter, which is drawn from the perpendicular bisectors of each side and likely outside the triangle. I mean, this is outside the triangle because the triangle is obtuse, and outside of the triangle, and is outside of the triangle because the triangle is obtuse. The circumcenter is equidistant from the vertices. Now, I mentioned that from a previous set of problems. Now, I over-explain when I do typing. I don't expect you to do that. I expect you to paraphrase. I don't know, let ChatGPT paraphrase it for you. I couldn't care less. But circumcenter would be, it would essentially be the same thing as far like the midpoint. It's not the same thing. But the midpoints here are a good start because if I could draw ideal perpendicular lines from these, like this one's perpendicular line would kind of look like that. Let's kind of pretend like another perpendicular line would be, like, I don't know, kind of that-ish. So perpendicular bisectors right here, boom, boom, and obviously the third one would be drawn somewhere. This would be more so the circumcenter. This is where you'd want to place P. So P, now, if I did draw it correctly, say, P would now be equidistant from here, here, and here. These would then ideally be the same length. And they kind of look close to the same length there. That's where P would want to be instead on that one. And that's part B. All right, guys, and that is it. Now, that doesn't guarantee that it covers everything. These quiz things can kind of go a little different, a little haywire. You could tell that those 3 in-center questions were all kind of the same. Not much Pythagorean theorem or anything was used. We actually got to use it later for an in-center questions. That was fine, but not everything was covered. I know I did a whole lot more then. We did do a proof. We did use graphs, and we did some basic math things with solving for x. I did enjoy those. Those were fun. But guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. If you still need to find a very specific problem, check the timestamps down below in the description section here, and you can also find a PDF of this very problem set. Take care. I will see you in the next one.